Hi, everybody. Today we are going to create our very first machine learning model. We are going to be dealing with regression. To be specific, today we will learn about linear regression. So let's recall what regression was. Regression deals with predicting a quantity or a real value as our outcome. So, for example, predicting the price of stocks or predicting the price of a house. Classification, on the other hand, deals with predicting a label. For example, given an image, we can try to predict whether the image belongs to the dog or to the cat. In this case, assume we have a function for the outcome. For example, let's say the price of a house, which we usually refer to it as y. So price will depend on a number of features, right? Like the area that the house belongs to, the size of the house, the number of rooms in the house, which we refer to as x or the features. So the price of the house, y, can be a function of x, which is the features, plus some error rate. And that is how we represent a regression model. So as I mentioned before, today we'll be dealing with linear regression. Now you're probably getting scared of the mathematical equation that you see. Well, don't be scared. We're going to break it down for you. So the function of x and omegas, which is also referred to as y or the output quantity, for example, the price of the house, would be linearly dependent on its features. For example, the number of rooms in the house. So in a two-dimensional case, it results in a simple line, where if the number of rooms increase, your price of the house will increase. In a three-dimensional case, it would look like a plane, and in an n-dimensional case, it's probably hard to visualize, but the equation remains the same, where your price of the house is dependent on multiple features like number of rooms in the house, number of floors in the house, the tax of the area, etc., which is represented by omega 0 plus omega 1 x1 plus omega 2 x2, and so on. Now, we are going to learn what these omega 0, omega 1, omega 2, etc. are in the coming slides. So linear regression is basically a way to predict a real value known as the dependent variable or the outcome, or we refer to as y, based on the independent variables or the features that we represent as x. So for example, when we want to predict the price of a house, that will be our dependent variable y, and based on the number of rooms in the house or the number of floors in the house, which are the independent variables or the features, or we refer to them as x. So linear regression basically assumes that the relationship between the dependent variable and the independent variable is linear, and we can use it for forecasting stocks, prices, and so on. It's a great model to use when the data has some linear behavior, and it can be also used as a baseline before you go into more complex models. So in the most simple case of linear regression, where you only have one feature, for example, we are trying to predict the price of the house, and we only have to feature number of rooms in the house. So it will be represented by a line, and there are two parameters: slope, which is also represented as omega 1, and intercept, which is represented as omega 0 in our equation before. So the slope is a number that indicates how slanted the regression line is and the direction in which it stands. So for example, if we will assume that if the number of rooms in a house are more, the price of the house should be more. And intercept is when the feature value is 0. What is the value of our output variable? So for example, if there are no rooms in the house, you can assume that's an empty land. What's the price of that land? So before we move on to the coding and dissecting linear regression further, let's talk about the library that we'll be using, which is scikit-learn. So scikit-learn is a Python library that provides a number of supervised and unsupervised machine learning algorithms that have already been implemented for us, so we don't have to implement them from scratch. But the library is not focused on modeling the data. For that, we use NumPy and Pandas. So a few things let's highlight about scikit-learn or sklearn. So it has clustering, which is a way of grouping unlabeled data such as k-means. We can perform cross-validation to estimate the performance of our models. It has built-in data sets for us so that we can test multiple algorithms and learn from them using these data sets. It has ensemble methods, which is where we combine multiple machine learning models to come up with a better model. We are going to talk about this later in the course. It also helps us in feature selection, which is which features should I use that will give me the best results. and it helps us in parameter tuning. So getting the best parameters for my model and so on. It has a very good documentation as well, and that's why we will stick with scikit-learn. So why should we use scikit-learn? Well, firstly, because of the documentation and the usability. Scikit-learn has amazing documentation and tons of examples to help guide you through its massive library. So any algorithm that you want to implement which is present in this library, it will have a detailed explanation as well as an example on how to implement it. It is used by the machine learning community, which means you will have tons of resources and references when you use scikit-learn, and provides a range of algorithms already implemented for us through a consistent interface. So to learn about linear regression, we'll be using the Boston dataset. It is one of the predefined dataset in scikit-learn, and you can look at the details that from the link that has been provided. So loading the dataset in scikit-learn is very easy. So we will verify the shape of that data based on the specifications that were given to us by scikit-learn, which is it should have 506 samples. There should be 13 features, all real and positive, and the target would be between 5 and 50. So how do we import our data in scikit-learn? Well, firstly, we import our library. So we import sklearn, and we also import datasets, which are predefined datasets using from sklearn import datasets. After importing our library, the first thing we need to do is load our dataset. To do that, we'll use the function load underscore Boston, which will load the Boston dataset into our variable called Boston. Now we will use the typical X for features and Y for target variable representation. So X will contain Boston.data and Y will contain our target variable. Now just to confirm whether we have loaded the data correctly, let's have a look at the shape of our X and Y. So X has 506 rows and 13 columns. So 13 columns is our features and 506 is the number of samples. And Y contains 506 samples, which is consistent with the documentation provided to us by scikit-learn. So here are the details of the dataset that we are dealing with today, which is the Boston dataset. We are trying to predict the price of the house in Boston given a set of features. As you can see, the details of each of these features. For example, we have crime, which is per capita crime rate by town. We have RM, which is the average number of rooms per dwelling. We have tax, which is full property tax rate per $10,000, and so on. So these are our features, and given the value of these features, we are trying to predict what would be the price of the house in Boston. So let's try to put our data in a format that is easy to read and something that we know. So for that, we will put our data into the data frame format. First of all, we will import the pandas library and we will put our features into the data frame, and the columns will be the Boston.feature names. And our target variable, which is called the price, will be represented by Y. And as you can see, the first 5 instances of our data where you have the values of the features and the target variable, which is the price. So the first thing to do as a data scientist or a machine learning engineer when you're given a set of data is to ask questions about that data. So for this particular case, the general question would be, what is the price of the house given the data that I have? Now, these questions can become more specific. For example, is there a relationship between highway access and the price? Does an older house mean a higher price? Do more number of rooms correlate to crime per capita? So we now have several variables, right, that could factor into the pricing of the house. How can we determine which one of these variables are useful and which ones are useless? So the answer to the question of which variables can be used and which variables can be discarded in linear regression is correlation. Correlation measures the strength of the linear relationship between two independent variables. And you can use this value to basically discard some of your features which have no correlation with the outcome that you're trying to predict. So correlation can be positive, it can be negative, or it's possible there is no correlation between the two. Typically, the value of correlation lies between -1 and 1, -1 representing absolute negative correlation, and +1 representing absolute positive correlation. So, for example, the GPA of a student would be highly correlated positively with the number of hours a student studied. So, as the number of hours the student studied increases, ideally speaking, his GPA should increase. Another example for a negative correlation would be the GPA versus the number of hours student procrastinated. So as the number of hours student procrastinated increases, his GPA should decrease. And it's possible that there was no correlation between two features, for example, GPA versus the price of the stocks. And in that case, the value would probably be close to zero, and you could probably discard that particular variable if that is the case. Now, to find the correlation for our dataset, which is the Boston dataset, we're going to import a few libraries so that we can show the correlation matrix in a easy, readable form. So we're going to import NumPy, we're going to import Seaborn and Matplotlib. The first thing we're going to do is we're going to compute the correlation matrix using df.corr. Now this function computes the correlation between each of our features. So we have 14 features. So that will result in a 14 by 14 matrix. And then we are showing them in a heat map using the Seaborn library. Now, as you can see, the diagonals of this matrix or of this figure is all 1. And this 1 represents the correlation between the feature itself. Now you can see crime with crime, the correlation is 1, Zn with Zn, the correlation is 1, and so on. So the whole diagonal is 1. Anything above that diagonal is the exact mirror copy of what's below the diagonal. So for example, if you have a look at row 2, column 1, Zn with correlation with crime, it's negative 0.2. And that is exactly the same with row 1, column 2. Similarly, row 3, column 1 would be exactly the same as row 1, column 3. So I hope it's clear that they are mirror images of each other. Now to discard some features from your model, what you can see is if there is a correlation between your price and any feature that is very close to zero. In our case, there's probably none, but there's CAS, which is a very low correlated feature with the price. And the highest correlated feature would be LSTAT, RM, and so on. So this is how you read a correlation matrix and display it in a format that's easy to read and is very helpful for you to understand your data and which features you can actually discard. Let's come back to the most basic version of linear regression called univariate linear regression or linear regression with only one feature. Now we know with only one feature, the output is basically a line. Now this line represents the line that reduces the sum of squared errors. Now a squared error is basically a difference between our actual value, y, minus our predicted value, which is represented by y hat, and we square them. So for example, let's say our actual value of the price of the house was 25, and let's say our prediction was 23. So the error is 25 minus 23, which is 2 squared of it, which is 4. So that is the error for one sample. Now, assuming that you have n samples, you will have n errors. So this line is the line that reduces the combined version of all those errors, and that is what linear regression is. So let's unpack what we just discussed about linear regression in a little bit more detail. A simple linear regression, also called a univariate linear regression, is an approach where you only have one single feature. And using that single feature, we are trying to predict a quantity, in our case, the price of the house. So y is the response, and y of I is the house price for the ith data point. In our dataset, we have about 500 data points. So for example, y of 100 would represent the price of the 100th house in our dataset. Now x is our feature, right? It can be any feature from our dataset. For example, the pupil teacher ratio in the area where the house is. So x of 100 will represent the value of pupil teacher ratio of the 100th house. Omega 0 is the intercept as we discussed before. So when our feature x is 0, what is the value of our house? And omega 1 is the coefficient or the slope, which is a number that indicates how slant the regression line is and the direction in which it slants. So for example, assuming that the age is positively correlated with the price of the house. If the age of the house was old, the price should be higher, and that is represented by omega 1. So that is what linear regression is, which is determining these two parameters, omega 0 and omega 1. And to create a model, we should learn these values or these coefficients. And once we have learned these coefficients, we can use the model to predict the price of the house. So the question you guys might be asking now is, how do you learn the model coefficients? So now that we know the equation of linear regression, which is y equals omega 0 plus omega 1x, how do I determine what omega 0 is and what omega 1 is such that the sum of squared error is minimum? Well, to do that, we use some calculus to find the solution to be as follows. Omega 1 is just the sum over all the samples, xi, which is the feature that we're using, for example, the age of the house, minus the mean of that feature, multiplied by yi, minus the mean of the price of the house, divided by the sum over all the samples, the feature minus the mean of that feature squared. Then we can find omega 0 by y mean, which is the mean of the price of the house, minus omega 1 times x mean, which is the mean of the feature that we are using, for example, the age of the house. So don't get too worried about the equation that you just saw. It looks scary, but we won't be implementing it ourselves. Scikit-learn has already done that for us. But let's try to see how we can build a linear regression model using the Boston dataset. So let's take a single feature and let's take our target, which is the price of the house, to build a simple linear regression model. So for our feature, we will use the RM feature, which is the average number of rooms per dwelling. So this slide represents all the steps you need to follow to build your linear regression model. Pay attention because you will follow the same steps for building any other machine learning model in scikit-learn. So the first step is calling the libraries. So from sklearn.linearModel, we are going to import linear regression. From model selection, we are going to import train test split function that will allow us to split our data into training and test. From sklearn.metrics, we are going to import a metric that will help us validate how good or bad our model is. In our case, we are going to use mean squared error. Step 2 is to define your feature and target variable, assuming that your data is ready for modeling. In our case, we are going to use RM as our feature and the price as our target variable y. Now note that we have to reshape these two variables x and y, otherwise you might get an error when you're using scikit-learn. If you use multiple features that come from your pandas data frame, you would not have to reshape them. But if you use a single feature, then you would have to reshape them. Step 3 is to split your data into train and test. To do that, we will use the train test split function. Now it gives us four outputs: xtrain, which is the feature of our training set; xtest, which is the feature of our test set; ytrain, which is the target variable or the price of the house of our training set; and ytest is the price of the house of our test set. Now, how do we know how much data goes into training and test? Well, that is defined by this parameter called test underscore size. In our case, we are saying 33% of our data should belong to our test data. After this step, all you need to do is define your model. In our case, we're going to use a linear regression model and save it in a variable called LR. To train your model, you just call the fit function and inside it, give your training dataset with your feature and your label. Once you finish executing the steps, what the model does is it determines the value of omega 0 and omega 1 based on the formula we just saw above. After training a model, all we need to do is to check how good our model is. To do that, we are going to predict on our test set and see what the error is. In our case, we get a mean squared error of 44.60, which is not too bad. The last step is to interpret your model. which is interpreting the coefficients of your linear regression model. In our case, we only had one feature, which was the RM feature. So our model has only one coefficient, which is 9.28, ignoring the intercept. Now, what does this coefficient of 9.28 means? What this means is, assuming if we ignore the intercept, if our RM value was 1, our price of the house would be 9.28. If the RM value was 2, our price of the house would increase by 9.28 times 2, which would be about 18, and so on. So I hope it makes it a little clearer on how to interpret your linear regression model and how to implement it in Python. So to visualize how good or bad our model was doing for each of the sample in our test set, what we can do is we can plot a graph. So in this case, what we have is on the x-axis, we have the original or the true values, whereas on the y-axis, we have the predicted values. And you can see sometimes we are off. Ideally, what we would want is to have all of these points on the black line. So we saw how good our linear regression model was with one feature, RM. What if we want to use multiple features? Well, let's see. Let's try to add age and text into our feature space and perform linear regression to see if our mean squared error would decrease or not. To do that, we will follow the exact same steps as before. We're going to define our x and y variable. We split our data into training and test. In our case, again, we will have 33% of our data into the test set. We will define our linear regression model and train the model. We will calculate the omega 0 and omega 1, omega 2, omega 3 for our linear regression model based on our training set. After fitting the model, we will see how good our model is by predicting on the test set. And hey, our mean squared error decreased from 44 to about 39. Now you see, now we have three coefficients, which is minus 0.03, minus 0.01, and 8. Again, you can see RM has a positive impact on the price of the house, whereas the age and the tax have a negative impact on the price of the house. So if the age of the house increases, the price of the house would decrease. If the tax increases, the price of the house decreases by that coefficient. And if RM increases, the price of the house increases based on that coefficient. So we tried with just three input features. What I would want you guys to do is try it out with a bunch of features and see if you can improve the mean squared error by a combination of different features.